Hey class, let's try another one here. This is one of the harder ones. This is from the university physics book. It's number 70. It's got this rider going in here. Let's read this one together. It says, part of riding a bicycle involves leaning at the correct angle to make the turn as seen below. And to be stable, the force exerted on the ground must be in line through the center of gravity. Now let me pause right there because we aren't quite there yet in the lectures, but I think that's what we're going to do real soon. It's the chapter after the next. If you had something like, these forces pushing and they're not balanced and along the center of gravity, and they would like offshoot here, let's say the center of gravity was down here, so you're leaning too much. This would tend to push you and make you kind of rotate, and that's our next discussion. We've done a lot of problems where we have just translational motion, but we really haven't got a chance yet to do that rotation, and those are a little harder, but that'll be kind of my tease into it, that if I lean too much, this actually just makes things worse. Or not enough, it pushes me up. So more on those in a minute. We'll just take their word for it, that to be stable, the force exerted on the ground must be in line through the center of gravity. So they're looking at this force from the ground, F, and it's going through the center of gravity. Okay. The force on the bicycle wheels can be resolved into two perpendicular components. The friction, which is parallel to the road. So this is the total force, but this right here is the frictional force. So parallel to the road, this must be supplying the centripetal force, and a vertical normal force, which must be equal to the system's weight. That's a nice hint, but I kind of wish they'd have left that off. That's kind of what we want to show. It says show that theta, as defined, and so they're talking about this angle, the tilt angle, so how much you would have to lean from the vertical, so that tilt angle. Show that theta is related to the speed v and the radius of the curve in the same way as for an ideal banked road. That is, theta is the inverse tangent of v squared over rg. And then calculate theta for somebody riding at 12 meters per second, turning with a radius of 30 meters, as is done in a race. All right. So, like all these problems, my step one is to say, do you got a good physical picture of what's going on? And I think so. I think we got a rider here, and we're going to say that there's really just kind of the force of gravity here, the weight, and everything touching it. What's touching it is only the road, and the road then is going to have two components, if you will. It's going to have an upward force, which is perpendicular to the road. We call that a normal, and then one parallel to the road, which we called friction. And then, of course, we move on to the free body diagram, and this one even helped us with the free body diagram. This one is saying that we have its weight, which would be mg, and then we would have the force from the ground, which I'm going to put as a dotted line. And the reason I'm going to put it as a dotted line is I think I'll start this problem with what they're thinking is that this force, the total force from the road, is made out of two pieces, a part that is perpendicular to the road and a part that is parallel to the road. And so I'm going to say this is made up of a normal force and a frictional force, which I'll just call F. Now, we can move on to step 3, which I call writing out the equations. But one of the first steps of writing out the equation is picking your grid. And as you've heard me say on many other problems, try to pick the grid, especially if you know the direction of the acceleration, so that one of your axes is along that direction. It makes the math so much simpler. So in this case, because we know the rider is going in a circle, we know that there would be an acceleration of v squared over r, and it would be towards the center of the circle. So maybe it's worth coming back to the physical picture and saying, so where is the center of the circle? And so you got to kind of picture this in 3 dimensions where the rider's coming out, and the center would be somewhere right here. But I want you to see it's along the traditional x-axis. And it's because it's along the traditional x-axis that I will also set up the traditional XY grid. I will not rotate it down the hill or anything. Okay. So then, knowing that's my grid, I can say, let's add up the forces in the x direction, and let's add up the forces in the y direction. All right, so in the x direction, you would say, or maybe I should do force by force. You begin to see why now I was kind of thinking maybe we should take the force from the road and look at its 2 components. Because if I take the force from the road, this one, F, is the amount in the x direction, and the normal force is the amount in the y direction. So this dotted line is really the combination of these 2. And so I hope you don't kind of see this as 3 forces or even 4 forces. It's really saying there's 2. There is the weight and the contact with the road. But the contact with the road is the 2 pieces that we keep talking about separately, the normal force and the parallel force, that is the friction. All right, so the force from the road, this would be the x component from the force from the road, and this would be the y component from the force from the road. Now, the other force is the weight of it. The weight is all down, so in the x direction, it's 0, and in the y direction, it's minus mg. And then those are each of the 2 forces with the 2 components. So 2 forces and the 2 x components, and the 2 forces and the 2 y components. That has to equal to mass times, and again, this is the advantage of setting up the x-axis towards the center of the circle. This would be a plus v squared over r. The v squared over r because it's going in a circle, and the plus is because the center of the circle is in the plus direction. Now, in the y direction, it does not move upward or downward, so the acceleration in the y direction is equal to 0. Okay. And so that resolves to normal force is equal to mg, and frictional force is equal to mv squared over r. So there's not much math to do to solve that. Although, keep in mind, the question was not to find the individual forces, but this angle. So looking at this angle and maybe pointing it out in my picture, see if the black stands out, but in my picture, this would be the angle theta. So the tangent of theta would be the opposite, which is the F force. So if I think about, these 2 added together, so I'm just going to kind of mentally translate it up to here so I can see it better. Remember, these diagrams don't mean position, so I can put it anywhere I want. So I'm going to put it up here, and I can see this would be the adjacent to the angle theta, and this would be the opposite. And the definition of tangent is opposite over the adjacent. So the opposite, as we just described, the frictional force, is this mv squared over r. And the adjacent is the normal force. The 2 m's would cancel off, and I would get, from the first factor, or the numerator, v squared over r. Then the g, I can make it a compound fraction, so I can flip and multiply. And so that becomes v squared over rg. And then finally, taking the inverse tangent of both sides. So I've got tangent, and if I take the inverse tangent, that undoes it. Those are inverse operators, kind of like adding 5 and subtracting 5, or squaring and then square rooting. Those are inverse operations, or multiplying and then dividing. You end up back where you started. So if you take the inverse tangent of a tangent, you just get theta. That's how you undo a tangent function. Of course, you got to do it to both sides. So this would be the arctangent of v squared over rg. And then, lo and behold, we got what they were asking for. What angle is it? And I think I can, well, I'm going to try to save a little sheet of paper. Actually, maybe I'll just do this on the back. So to find that angle for B, theta, it's going to be the arctangent, and then look at our numbers. It says for B, calculate this angle when you're traveling at 12 meters per second, and your radius is 30 meters. So I'm going to put a 30 and a 9.8. And so grabbing a calculator, I've got 12 squared, first divided by a 30, then divided by a 9.8. Okay, so then I can take the inverse tangent or arctangent of that number. And it looks like I would be leaning over at an angle not real far. I would have kind of expected more. They say the radius is 30. They make it sound like that's a normal value, but maybe that's a normal value for an outdoor race, and I was thinking indoor cycling because, well, then you couldn't lean enough. That's why they banked the turns on an indoor race here. So anyways, that's a whole nother story. This is a flat ground outdoor race here. Anyways, so there's the angle. All right. Hope that helps.